Welcome to UVM Coffee Machine, learning UVM through coffee orders. If you love coffee and want to finally understand UVM in a simple, visual way, you're in the right place. In this video, we're going to break down the universal verification methodology, using something everyone understands, ordering coffee. No heavy syntax, no complicated jargon, just pure concepts. The goal of this tutorial is to help you understand the core UVM components: the DUT, the interface, the transaction or sequence item, the sequencer, driver, monitor, scoreboard, agent, environment, sequences, and the overall test structure. By the end, you'll know exactly how all these pieces work together. UVM is built entirely on OOP principles, which means components are extended, reused, and communicate through a structured hierarchy. I'll show you how those OOP ideas translate naturally into our coffee machine analogy. And just to be clear, we're focusing on concepts, not syntax. Some parts of UVM are written a certain way simply because that's the standard, and we won't waste time on boilerplate code. Instead, whenever real reasoning, logic, or design decisions are involved, I'll explain them in a simple and intuitive way. The goal is simple: to understand the flow, the architecture, and gain practical familiarity with UVM, all through the journey of making a great cup of coffee. Let's start with our coffee machine system. This is the DUT, the design under test, that we want to verify. The inputs to our machine are simple. We have the size, which can be small or large. We have a with milk input, and we have a with foam input. And of course, we have a clock that synchronizes everything. The output is the coffee type, the drink that the machine produces based on the inputs. There is one important rule. Once an order is received, the machine needs exactly one clock cycle to prepare the coffee and produce the correct output. Here are the drinks our coffee machine supports: espresso, small, no milk, no foam; latte, large, with milk, no foam; cappuccino, large, with milk, with foam; and for all other input combinations, the output is none. Let's walk through an example. Suppose the inputs are: size is large, with milk is 1, and with foam is 0. That combination represents a latte order. After one clock cycle, the machine outputs latte. And one more important note: in real verification work, we almost never receive the designer's code. We only get a description of the intended functionality, what the machine should do. This is because in many companies, design and verification happen in parallel. While the designers are still writing the RTL, the verification team is already building the test bench. So our job is to verify the behavior, not the implementation. We begin by defining the interface, the set of signals that connects our test bench to the DUT. You can think of an interface as the control panel of the coffee machine, the buttons you press to choose the drink, and the indicators that show what the machine produced. In our example, we create an interface called coffee_if. It receives the clock input, keeping everything synchronized. Inside the interface, we list all the signals the DUT expects: the size input, where 0 represents small and 1 represents large; the with milk signal, the with foam signal; and finally the coffee_type output, which tells us whether the machine made an espresso, a latte, a cappuccino, or none. Before we start building our UVM test bench, let's look at the general structure of this template. Everything here lives inside a package called coffee package. Why do we use a package? In UVM, almost all of our components are split across many files: the transaction, the sequence, the driver, the monitor, the scoreboard, the environment, and so on. By placing them inside a single package, we collect all related classes into one logical group. It also lets other files import everything at once, so we can simply write import coffee package and immediately get access to every UVM component we defined. At the top of the package, we import the UVM library and include the UVM macros. These macros register our classes with the factory, allowing UVM to construct, override, and configure them dynamically. The first real section is the enumerations. Enumerations are a clean way to give names to values that would otherwise be just numbers. For example, we define size underscore e with small and large. Instead of remembering that 0 means small and 1 means large, we use meaningful names that make the code easier to read and much harder to mess up. Next, we define coffee underscore type underscore e, which describes the possible outputs of our coffee machine: none, espresso, latte, and cappuccino. Again, these names are easier to understand than raw numbers, and they make debugging far more intuitive. From here, we list every major UVM component we're going to build. Each class is declared now, but intentionally left empty. The order of the components inside the package is not random. Some pieces need to be defined before others, so the package is arranged in a very specific bottom to top order. At the very bottom, we start with the transaction, because almost every other component depends on it. Next comes the sequencer, which needs to know the type of transaction it will handle. Then the driver, which also relies on the transaction class to understand what it needs to drive onto the interface. After that, we define the monitor, which reports what it observes back to the rest of the test bench. These three components, sequencer, driver, and monitor, are grouped together later inside the agent, so the agent must appear after all of them are defined. Then we define the scoreboard, which needs information from the monitor to check correctness. Next is the environment. The environment connects and instantiates the agent, the scoreboard, and any other verification components, so it must appear after all of them are declared. Only at this point do we talk about sequences, because sequences reference both the transaction and the sequencer. And since sequences are created and started inside the test, the sequence section naturally comes before the test itself. Finally, at the very end of the package, we define the test. The top-level component that configures the environment, creates the sequences, and launches the entire verification flow. This entire file is the blueprint of our UVM test bench. Now that the structure is in place, we're going to go through each component one by one and fill in exactly what it does. If you found this content valuable so far, consider supporting the channel by subscribing. It really helps the channel grow. The transaction class represents a single coffee order. Whenever we want the test bench to request a drink from the coffee machine, we do it by creating one of these transaction objects. Each transaction contains the fields that describe an order: the size, whether it includes milk, whether it includes foam, and the expected coffee type that we will later compare against the DUT output. These fields are marked as random, which allows the test bench to automatically generate many different drink combinations. This helps us explore a variety of inputs without writing each one manually. There is also a constraint. If foam is requested, milk must be included. This matches how our coffee machine behaves, because you can't add foam without milk. Finally, the print function displays the order details whenever the test bench needs to log what was created. This is useful for debugging and understanding what the simulation is doing. The sequencer is the component that manages the flow of transactions to the driver. It doesn't change the data, and it doesn't know anything about the DUT. Its role is to deliver the next coffee order whenever the driver is ready. In our coffee machine analogy, the sequencer behaves like the person organizing the coffee orders and handing them out one at a time to the barista. The sequencer is parameterized with the transaction type, so it knows exactly what kind of objects it will send. Now let's look at the driver. The driver is responsible for taking a coffee transaction and driving its fields onto the interface signals of the DUT. First, the driver receives a virtual interface through the UVM configuration database. This gives it direct access to the pins of the coffee machine. Inside the run phase, the driver runs forever. Each time the sequencer provides a new transaction, the driver waits for the next rising clock edge and then places all the transaction fields onto the interface: the size, the with milk bit, and the with foam bit. After driving the inputs, the driver calls item_done to notify the sequencer that this transaction has been fully processed. Next, we look at the monitor. The monitor also receives the virtual interface, so it can observe all the signals connected to the coffee machine. It publishes observations using an analysis port, so other components, like the scoreboard, can receive them. In the run phase, the monitor continuously watches the interface at every clock cycle. It keeps track of the inputs from the previous cycle because the coffee machine produces its output one cycle later. On each rising clock edge, the monitor checks the current output and pairs it with the inputs seen in the previous cycle. It packages this information into a transaction and sends it through the analysis port. The scoreboard is responsible for checking whether the coffee machine produced the correct drink. The monitor sends completed transactions into the scoreboard through an analysis port. Every time the scoreboard receives a transaction, the write function is called with the observed values. Inside the scoreboard, we calculate what the expected coffee type should be, based on the size, the milk selection, and the foam selection. We simply look at the three input fields and match them to the correct drink. If the output from the DUT does not match the expected value, the scoreboard reports an error. If it does match, we log an informational message saying the coffee is correct. This is the main checking component in our test bench. It verifies that the machine behaves exactly as the specification describes. The agent bundles together all the components that interact with the interface. Inside the agent, we create three objects: the sequencer, the driver, and the monitor. These are the core pieces that generate transactions, drive the DUT, and observe the outputs. During the connect phase, we connect the driver's sequence port to the sequencer's export. This connection allows the driver to receive coffee transactions directly from the sequencer. The agent behaves like a small subsystem inside the environment. It holds everything needed to stimulate and observe the DUT using the interface. This section defines the environment, the top-level container that gathers all of our verification components in one place. Inside the environment, we declare two members: the coffee agent, which contains the sequencer, driver, and monitor, and the coffee scoreboard, which checks the correctness of the coffee machine's output. The agent is responsible for generating stimulus and monitoring activity, while the scoreboard receives every transaction that the monitor observes through the analysis port. This means that every time the monitor detects a coffee order and the resulting output, it forwards that information directly to the scoreboard for checking. After defining the environment, we move on to the sequence. A sequence generates multiple coffee orders and sends them to the sequencer. In the body of the sequence, we repeat the process 20 times. We create a new transaction, start it, randomize its fields, and then send it forward to be executed. Each transaction represents one new coffee order for the machine to process. This final section defines the test, the topmost component in the entire UVM structure. Inside the test, we declare two objects: the coffee environment, which contains the agent and the scoreboard, and the coffee sequence, which will generate the actual coffee orders. The environment is constructed first because we need the verification setup ready before any orders can be generated. Then we create the sequence, which will later run on the sequencer inside the agent. In the run phase, the test controls the full simulation flow. We raise an objection to keep the simulation alive, start the sequence on the agent sequencer, and allow time for the coffee machine to process all orders. After the sequence finishes, and enough time has passed for the last outputs to appear, the objection is dropped, signaling that the test is complete. Now let's take a look at the test bench code that ties everything together. We begin by including the UVM macros and importing our coffee package, which contains all of the UVM components we built earlier. We generate a clock that toggles every 5 nanoseconds. This clock drives both the DUT and the interface. Next, we instantiate the interface, coffee_if, which holds all the signals the test bench uses to communicate with the coffee machine. Then we instantiate the DUT itself, named coffee_machine, and connect its inputs and outputs directly to the interface signals. In the initial block, we configure the virtual interface. We pass the interface to the driver and the monitor using the UVM configuration database, so both components have access to the DUT signals. Finally, we start the test by calling run_test with the name coffee_test. With the test bench set up, we can walk through the simulation flow. The sequence generates a coffee order and sends it to the sequencer. The sequencer passes that order to the driver. The driver acts like the barista, pressing the machine's buttons. On the next rising edge of the clock, it drives the order into the DUT through the interface, the drink size, whether it includes milk, and whether it includes foam. While the driver is sending orders, the monitor is watching both the inputs and the outputs of the machine. On each cycle, it pairs the previous order with the coffee produced by the DUT and sends that combined information into the scoreboard. The scoreboard calculates what the expected coffee should be based on the order that was placed. It compares that expected result with the actual result coming from the DUT. If they match, we get a confirmation message. As the simulation runs, you can see the test bench move smoothly from one order to the next, generating, driving, monitoring, checking, and validating the behavior of the coffee machine. If the scoreboard reports a mismatch, we immediately know there is a bug in the design. Because the monitor prints every transaction it observes, we can inspect the exact order that caused the issue, see the output the machine produced, and use that information to pinpoint the root cause. We've reached the summary of our UVM coffee machine example. We created a complete UVM verification environment using a simple and intuitive analogy: ordering coffee. At the center, we had our DUT, the coffee machine. It receives an order, the size, whether it has milk, and whether it has foam. And exactly one clock cycle later, it produces the coffee type. To verify this behavior, we constructed the full set of UVM components. The interface acts as the control panel that connects the test bench to the machine. The transaction represents a single coffee order. The sequencer delivers orders one at a time. The driver behaves like the barista pressing the machine's buttons. The monitor watches both the order and the result. The scoreboard predicts what the drink should be and compares that prediction with what the DUT actually produced. The agent bundles the sequencer, driver, and monitor into one block. The environment brings the agent and the scoreboard together into a full verification setup. The test creates the sequence of orders and starts the entire simulation. Here are the key takeaways. UVM is a structured OOP-based methodology. Each component has a clear and specific responsibility. Once you understand the flow, you understand how UVM works. And now, you do.